So as you can see, thermal analysis is just a natural extension of doing structural analysis. The same clicks, similar interface, and they are very well integrated. Next, I'd like to demonstrate motion analysis, otherwise known as rigid body dynamics or multi-body dynamics. This is where we assume all of our bodies in the model are rigid, and then we have kinematic and force relationships defined between the different bodies. And in this case, we reuse the SOLIDWORKS mate constraints, and then we can apply motors and such to optimize springs and dampers, simulate cam drives, latch mechanisms, study linkage movement, and calculate impact forces. Simulation Professional adds the event-based motion capability. So this is sort of a simple control system. In standard motion that would come with SOLIDWORKS Premium, all your forces and motions are essentially a function of time. With event-based motion, you can create virtual proximity sensors and other types of measurement sensors that will then trigger other actions to either turn on or turn off mates, change motor forces, turn motors off, etc. Next, we're going to use the loads from motion to calculate stresses in a component a couple different ways. And then lastly, we'll use those loads and those stresses to calculate the fatigue in one of the components of our motion analysis. To demonstrate SOLIDWORKS extensive motion capabilities, we're going to use the Homacho spreader model here. And as we see to the left, we have our motion feature manager, and we have a piston actuator, and we have forces on our test fixture that are resisting the motion of the spreader arms. And then we have solid body contact defined between the spreader arms and in the blocks. In addition, we have gravity applied to the model. So how do we go about building a motion model and then integrating event-based motion capabilities? So we'll start out with a blank motion model, and we have filters here to filter the driving parts of the model, that move, if we just want to look at result sets, etc. So we'll just filter on driving items, and then in addition we can also look at the motion model in multiple ways. We can control the different elements, the different motion components in a timeline fashion or using our sensors. And then we see we have motor constraints that we can create. So for example, I'm going to apply linear motion to the piston actuator. And that motion can be a function of a sensor, or we can define it as a function of time. So for instance, we can say open 60 millimeters in 10 seconds. And now we've added a motion to our model, and the next thing we might want to do is solve to just see what's the behavior of the model look like. So we hit the little calculator button here, and we see that our piston is traveling and the mechanism kinematics or connections are working the way they should be, but the blocks aren't moving because we need to define the contact between them. So if we move to our right, we'll see that we have contact sets that we can create between the different bodies. And then the stiffness of the contact event or behavior we can control by defining the two materials that are in contact. So let's say steel on steel. But we can also override these stiffnesses if we want. So this is the stiffness coefficient calculated automatically by SOLIDWORKS, but we also have the flexibility to modify that ourselves. And then to apply a resisting force, I'm going to apply a force to each of these blocks. We can reverse the direction. We get great feedback on the orientations of our forces and the directions of our motors. And then I'll apply the same force on the opposite face. And now we can once again test our model. Now the spreader arms, they're not penetrating through the blocks. The contact forces developed are a function of the coefficients calculated by SOLIDWORKS based on the material properties. And we have the spreader blocks are resisting the force. So we're emulating a test bench that we might use to validate our designs and determine what are the forces required to move the piston against a certain resisting force. And we can just replay the analysis. And now we'll see that there's also items in our timeline, and we can manipulate whether parts turn on or off, or connections turn on or off, or forces are modified by dropping keyframes in the timeline and suppressing different items. But we'll see event-based motion is an easier way to accomplish that. But why do we do a motion analysis? Well, we usually want to figure out the size of pistons to actuate assemblies, figuring out mechanical advantages or the loads through different parts to determine their stresses. So let's figure out the force that was required to open the spreader. So I can just select the motor that's doing the work and create a plot and say I want to look at my motor force. And here we see the force required at the piston to create the motion, and that will show up in our result sets. And then I can also look at forces through different connectors, for example. So let's see what mates are active on the arm. And I've got a hinge, and I might want to know what are the forces through that hinge. So we'll select reaction forces, and we'll just do magnitude, but we can choose directions. So now we can investigate the force through our different linkages. So far we've built up a quick motion model, and we've been driving it completely as a function of time. But if you've been working with SOLIDWORKS for a while, you might be familiar with different sensors. We can do measurement sensors, proximity sensors. For example, in this model, I've got a sensor created that tells me when the block is less than 1 millimeter to the end of the test fixture. And then I also have a sensor in the model that tells me when the piston is back to its home position. So we're going to use these sensors to make a more intelligent model. And this is called event-based motion. So before we saw a timeline-based motion model, now we're going to have a event-based motion table to look at. So in this model, I've added 2 motors. So when the blocks hit the end of their travel, these motors turn on and hold the blocks in position. And then when we reach that trigger, we also change the motion so that we reverse it so that the spreader is going to close. And then when the spreader comes back to its home position, we're going to stop the analysis. So we can see what that looks like. And slow that up. Okay, so now let's make some slight changes to this model. Instead of the simulation stopping when the piston comes back to its original position. I'm just going to tell our motor to stop moving. I could turn it off, which would then release that degree of freedom, but I still want to control that motion of the linear actuator. And then let's have another event occur. In this case, I'm going to deactivate a mate when our sensor is triggered for the home position. And now we're going to tell it to turn the lock constraint between the tip and the arm. We'll turn that off, and then gravity is going to do its job, and we're going to watch it fall out of the screen. And when the blocks hit the end of their travel, we're going to turn on another set of motors with 0 velocity, so that's going to hold them in position. We have a 1/10 of a second delay there. And then now the arms are coming back with the actuator at 15 millimeters per second. And the motion is stopped, and then we release the mate between the tip of the arm and the arm. So we don't need to know before the fact when things happen with respect to time. So now we can build more intelligent motion models to calculate both system level behavior, timing, interference detection, and then we can also use motion analysis to calculate stresses. We can calculate stresses due to motion loads in a couple of different ways. One way is we can view the stresses directly in the motion animation. We can select the part that we want to calculate stresses and which time frames during the motion analysis that we'd like to calculate them. And the other method is that we can import these motion loads for individual components for a single time step or multiple time frames directly into the part file and perform the stress analysis. And we're going to do that in a minute after we take a look at stresses as they are calculated as part of the motion analysis. We can see we can display deformation, factor of safety, and stresses, and then we can animate that directly during the simulation. And then we see the stresses go away after we lose the load by reversing the direction and holding the blocks in position. So let's take a look at the arm itself. So we see that within the ARM part file we have a simulation study where loads were automatically exported from motion and imported into structural analysis. And then all we have to do is just go ahead and run the analysis, and then we've got stress, displacement, strain, and just like everything else within a typical stress analysis, we can view the stress in multiple ways. We can look at an isoplot, and this helps us determine where the stresses are in the part and where we can remove material. But most importantly, we can also extend this into a fatigue analysis. And we see that we already have a fatigue model in the study, And the inputs to a fatigue analysis are a stress event and a number of cycles. Since this is linear analysis, we can scale the loads up or down. So I've assumed that we're dealing with a 5 times larger load and 100,000 cycles, and the output from stress is damage. And so anywhere we have damage over 100%, we're likely to see stress cracking. So this is nice. It's nice to be able to view the stresses in the motion analysis, but it's also very handy to be able to go ahead and further extend the analysis to calculate fatigue, which is the likelihood of developing cracks even though we might be staying under the yield strength of the material. So you can see it's very simple to take our loads from a motion analysis and extend that into a structural analysis to limit deflection and limit stresses, and then finally calculate the life or the amount of damage in our part. And all of this was accomplished using Simulation Professional Motion, event-based motion, and fatigue modules. So we've calculated the fatigue life of one of the parts in the Homatro spreader, but I'd like to investigate the handle of the spreader in a little bit of detail.